Hey guys, how are you doing? You might notice that my background is different, and it's because it is. Uh, yeah, I'm actually doing this from college, which is weird. There's another thing you'll notice is that this fan is constantly running, and that's because the storm is great and it doesn't have AC, so I need to have this thing going all the time to keep me from going insane. But don't worry, if it is distracting, you're not alone, it's distracting to me too. So that's awesome. I tried messing with some audio settings and like doing some suppression and whatnot, but it didn't do it perfectly, so either I messed it up or it's just not working. But it's most likely that I messed it up, so we'll see later, I guess. Hopefully this works right now. Yeah. I guess I'll show you guys the room later, I guess. Not right now. Let's see. So, hang on. Didn't mess with that. Speaking of that line of code, guessing it wasn't particularly the best preview of what's going on, but you know, the video, it's only like a small part of it. There will be more. Yeah, okay. So right now we have the educational round. As usual, I am fashionably late, but that's okay, because again, I am not really trying to do particularly well. So that is fine. Do not mean to click that. Hopefully that didn't actually mess with the audio. No, it's still doing the... Okay. Alright, so you have a string, each letter is A or B. A substring is a substring. You have a string, it is called balanced if A, the number of A's is equal to B. Find any non-empty balanced substring. Why? Why did I make it 50? So the point is just to like... Okay, well if there is a balanced substring, there will always be one of length 2. Because if you have all of one character, then you're not going to have anything. And if you have both characters at some point, then there will be a point where one character touches the opposite character. There has to be. So we can just look at that. So let's just do that pretty simply. Wait, does it give a length? No, it does. Okay. Read into n, and then to s. And we're going to iterate up to n minus 1. And we're doing that because we're accessing I plus 1, so we don't want to go out of bounds. Then we just print that if we find it. And otherwise, we print that there is nothing. Let us go. Test cases. I'm going to close Steam. I'm going to close this since this has been sucking. And I don't need that. I am trying OneNote out just because it's been recommended. I am still using my old text editor, which is fine. If you guys have strong feelings about other ones, maybe I'll look into other ones. 1, 2, 1, 2, 1, 2. Yeah, sounds right. That is nice tests. Let's do actually like 3, 5A, 5B, 3A, -1, -1. Yeah, okay, we're fine. I don't know why I'm checking that hard because it's just looking for a consecutive pair of unequal characters, but whatever. Wait, what? Oh yeah, I messed something up. Wait, what? Did I misread something? Oh, -1, -1. Okay. Sure. Lazy checker. Fine. looks fun. Maybe I'm gonna do that one this time. Last time I could skip to F, but this doesn't look fun. Okay, you have a chess tournament. Wait, how many solves does this have? It has 220 solves 12 minutes into the contest. That sounds awesome. A chess tournament will be held soon. N players will take part. Each participant will play one game, making sure sound is still going. Yep, each participant will play one game against every other participant. Sure, so tournament. Every game ends in a win and a loss, or a draw. So player wants to not lose any game. Every player wants to win at least one. Fun. Okay. So the particular players themselves don't really matter. It's more about the number of people that did it. So type 1 is annoying. Type 1 well actually wait, okay. So if we have two people, if we have no people with type 2, then we can make everyone draw each other, and that part's fine. If we have one person of type 1, then there is nobody they can win against, so it is impossible. I think that is the only case where it's impossible. And the other, yeah, here this illustrates that. And otherwise, if we have at least two people with, no wait. If there are two people with type 2, then it's also impossible. Because only one can beat the other, and then the other loses. So if there's one or two people with type 2, it's impossible. Otherwise, we can sort of arrange things in a cycle. How do I do this? I want to draw. Let's just do that. Okay. Sure. So basically, we're assuming like we have people like this, and these are all type 2. So basically, we're going to arrange them so that when this guy plays this guy, they win. It's basically just creating a cycle so that everyone wins against someone else in type 2. But other than that, everything else can be a draw. It doesn't really matter. Okay, so let's just do that. So I'm going to initialize a count array. Does give you n again. I'll make it 2. Okay, so Carmat 55. Actually, let's do it better. A string, that's not a car anyway. A string is an array of characters, so that is exactly what we want. Mat I is equal to string of length n, and the character is a draw. And we also need to set the interaction with itself to be an x. That is part of the rules. So now, if count 2 is equal to 1, no, sorry, count 1. You know what? For clarity's sake, I'll just make them the original numbers. So if the number of 2's we have is equal to 1, or we have 2 of them, then it is impossible. Because the cycle formation doesn't work. With one person, there's nobody they can win against at all, because everyone else is like, they don't want to lose at all, so they can't be beaten. And if there are 2 of them, then it's sort of the same situation. One can beat the other, but like, who does this guy beat then? They can't beat anyone, because nobody else wants to lose. So it's impossible for 1 and 2. Otherwise, count to is greater than or equal to 3. Then we make a cycle. So what I'm going to do is I'm going to just put all the characters of like 2 into like a list of indices. Si is equal to 2. Ins.push back I. And now we can sort of arrange a cycle between these. So equal to 0, I is less than ins.size, I plus plus. We're gonna make the next character I plus 1 mod ins.size. So it lets us overflow. The last index should match with the first one. So then mat I next is equal to a plus. This guy should be the next, and this guy should lose, and the next guy of course will lose to the I. I cannot type. You know, someone was asking me about how to remove typing inaccuracies, and you see how often I'm missing these keys. It's actually absurd. I think it should work. Yeah, okay. Let's try it. So 1 1 1, yep, perfect. 2 1, just stuff. And 4 2 1 2 2. So 2 beats 1. No, 1 beats 2. 2 beats 3. 3 beats 1. Yeah, that is exactly. Wait, why 3? Ins I, that's why. That is a good mistake. We should make the indices happen instead of the, instead of the index itself. That is important too, not making dumb things like that, dumb typos. So, why does 3 beat himself? What did I mess up? Oh, ins next as well. Yep. Be careful, guys. Or you'll be like me. At least I didn't submit this. That would have been a pain. Just small things you can overlook that end up screwing you over. So 1 beats 3, who beats 4, who beats 1. There we go. So again, we're doing this. We keep track of the counts. If there's 1 and 2, it's impossible. If otherwise, if there are at least 3, we're going to create the cycle of 2s and arrange them sort of in a circle. So like basically, this is the idea that I have. If the 2s are like this, then we're going to just do it like this, and then like this, and then like this. That's who beats who. Did I misread something too? Oh wait, I didn't mean to return here. Whoops. Because yeah, I was just printing a blank matrix. That doesn't make sense. Got a lot of output problems here, and that's kind of odd. Still. Token x equals does not correspond to pattern. What am I supposed to do? Oh, yes. Okay. Fine, I'll play by your rules. I actually don't know why I printed -1. That doesn't really make sense. So sure. Because it's a string anyway, so -1 doesn't really make sense. I'm not going to test that, because I'll just get wrong answer on test 1 again if it fails. There we go. Okay. Yeah, that got more solved over time. I guess it was just implementation. Not really sure. But anyway, let's do C. N people gathered to hold a jury meeting of the upcoming competition. The ith member of the jury came up with AI tasks. So the jury decides on the order that they will follow. Let that be a permutation P. If they have some tasks left, they tell, okay, so they do it in order. They tell one task to others. And so they go in order of the permutation. none of the jury members tell two or more of their own tasks in a row. Okay, so that will only happen if let's see. Well, if there's some big giant number. Oh, I see. Okay. So when let's find the condition for when someone tells two of their tasks in a row. Do this. I have no idea if that worked. Okay. What? What happened here? Can I just do like? Okay, yeah, that works. I don't know why I did a text box, but I guess that's fine. Do they have a lot of colors? Oh, they do have a lot of colors. Alright, cool. So when does this actually happen? If someone has two larger than everyone else, then that will happen. Because they will go around. If someone has like two larger than everyone else, for example, say we have like 5, 3, 1, 2, then they'll go around, everyone will tell theirs. This is like within the order of the permutation. So 5, 3, 1, 2, then they'll go around, say 3 turns pass, then you get 2, 0, 0, 0, right? And then this guy will go twice. So the question is, if that's the case, there are automatically no good permutations. If one person has 2 higher than everyone else. So we can set up by sorting the array because it doesn't really matter, and we can check that condition pretty easily. And the reason it doesn't matter is because we're looking for orderings anyway, so whatever order we process it in, it doesn't matter because any ordering won't change when we change our own ordering. Like, we're just thinking about the orderings in a different way, but they're still the same orderings of the same numbers. I don't know if that made sense, but I'm just saying we can sort, it's fine. Sorting is okay. So this is close to 720. So this looks like the only real case, because the others are just like random. So the ordering also matters. If some person is, let's say we have 5 here. So if we have 4 here, then this will be fine. But if we have 4 here, then let's move it down to 1, 2. And now this guy, so say 3 turns happen. Then this guy goes, then now we have 0, 2, and now this guy will go twice. So that's a problem. So the condition is not only that it's 2 greater than everyone else, but also that, like, it depends on the ordering of the other elements. Because 5, 4 is okay. We'll go 2, 1, then we'll have 1, 1, 1, 0, 0, 0, and it'll be fine. But otherwise it won't be. Okay, so we consider the highest element then, because the highest element is really what matters. The highest element is the only guy that could possibly go twice. So suppose the highest element is not unique. If we have 2 5s, then no matter what's going on here, no matter what's going on here, no matter what's going on here, this will happen. We'll do 4, 5, 10. We'll do 4, 5, 4, 4, dot, 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 like 1, 1, 0, 1, and then 0, 0. Everything will work out. So if the highest element is not unique, then we're good. Otherwise, the highest element is unique. And then what? Well, the highest element being unique, is this the best way to select something? I just want to delete it. I'm also messing with my volume, which I'm kind of scared about. Is this still picking up sound? I don't know. I don't want to touch the mic because it's like been messed with so many times. So now we assume the highest element is not unique. So for example, say again 5 is the highest element. So now what can we do to make it a good permutation? And it might actually be easier to ask what can we do to make it not a good permutation. And it will not be a good permutation if... Well, we're really interested in the elements that are 1 less than it. So all we care about are the 4s, because the 3s will always be outclassed. Like suppose we have 3, 5, then this will go down to 0, 2, and then they'll go twice. So the 3 doesn't affect anything on either side, of course. Well, actually, wait. Yeah, this will go down to 2, 0, and then nothing will happen. So we really only care about the elements that are 1 less. If there are none of them, every permutation is bad. So, yeah, that is sort of the condition I had before. But if there are some of them, then for the permutation to be bad, they all have to be before this guy. Yeah, so all of these guys have to be before this guy. So that, for example, we have like many 4s and then a 5. Then we go down to, wait, is that right? Yeah, then we go down to 0, 0, 2 eventually. That is the final turn. And then this guy would do 1 and then 0. I want to make sure I'm reading that problem right. Yeah. Okay, so... Wait, what is it? It's like hosting a contest? Yeah, okay. So, now the final part is... Like, what about otherwise? What if we have, like, some 4 over here? And then this will work out, because now, when this guy becomes its 2, this guy will still be 1s. So, instead of him going twice in a row, this will happen, then this will happen, and then we'll be fine. So, every element that's 1 less has to be before. And it's only good if at least one of the elements that are 1 less than the maximum is after. So we can count... So the number of permutations where every good guy is before is actually, like, not that many. Well, wait. Why does that happen? So here we have 3 3s, and somehow we get 3/4 of all permutations. So 1/4 doesn't work. Oh, yeah, okay. Wait, what? Yes. Okay. Yeah, okay. So, right, now we're just interested in how many permutations actually is this. How many permutations are there where we don't care about the other elements. They can do whatever they want. But we have this specific set of elements that we're interested in, and we're interested in this specific configuration. So, suppose there are, like, x 4s and a 5. So, like, it's like the count of 4s plus the count of 5s, or in particular the count of the count of the second maximum plus the count of the maximum. Then there are x factorial permutations of these numbers, but there are only... We know that C4 is equal to x minus 1 and C5 is equal to 1. That is, like, the condition. Okay, this writing is smooth. I like that. So there are x factorial in total, but this is the configuration that we want. So among here, there are x minus 1 factorial ways to arrange these 4s in their order. And all of these do not work. So the total number of permutations is x factorial minus x minus 1 factorial. That is the idea of it. So then everything else will work. So really, the answer is we take n factorial, except we have to account for these permutations not working. So we take n factorial, then essentially the ratio of permutations that work is this. Because there are x factorial permutations of this in total, but a certain amount of them don't work. So of these are the only ones that do work. So if these were the only elements, this would be the answer. This is the ratio of permutations that work. But we have all the other elements, but really it's sort of the same idea, that of all the permutations, like, these guys kind of don't matter. What really matters is this, like these numbers, and then we'll fill in the rest of the numbers after we make sure that these work. So this ratio sort of still stands. It's the number of permutations of these numbers times the number of ways to handle the rest of it. And the way to do that is, you can think of it as just putting the rest of the elements in is like the number of ways to permute n minus x elements. Because we have n minus x elements left to place, and it's sort of in reverse. The first one has 5 positions to be in, the second has 6, the second has 7, up to n. Actually, this might be x. Wait. I'm actually not sure. Combo. I can't spell. Yeah. Okay. Let's try that. Still can't spell. I forgot, like, empower. Oh, yeah, no, that's right. Okay, yeah, that's right. Wait, is that right? I think it shouldn't include x, is what I'm thinking. And I'm right about that. Well, actually, wait, should it? No, yeah, it should. Okay, yeah. Wait. I am lost. I think it should not include x, but... Oh, wait, okay. I'm thinking about this wrong. My bad. So... Yeah, okay, I'm thinking about this wrong. This quantity is the number of permutations we have that works among these. Then we multiply that by np, like n minus x minus 1, I think, so that it starts at x plus 1 and goes on. And then the total, like, this formula sort of simplifies to whatever this ratio is times n factorial. Because again, it's the ratio of things that work, and n factorial is the total number. I spent a long time trying to explain that. So, yeah, that's what's happening. Is the ratio of things that work times n factorial. So, we can start by computing this now. So yeah, let's just see. I think this formula still works, even if x is 1, just because 0 factorial is 1 as well, so that works pretty well. Let's see. What do the numbers go up to? 200,005. There's 200,000. Why does it put dots? I need to get rid of that. Seriously. This needs to be in here. Pre-computation. Mod is 10 to the 9th. Nope, it is not. It is the other number. EF15 mod, yeah. So let's go. Or NTT mod, I guess. FFT, I don't know. I don't think it uses that. I don't think it uses mod, actually. So yeah. So first thing is the count of the maximum number. Second thing is the count of the maximum number minus 1. So it's equal to fact So we're gonna go from n to y plus z exclusive, which is this quantity. It's npm minus x minus 1. I'm pretty sure it's minus 1. Yeah, it should be, so that it's n minus that, and therefore it's x plus 1. Because we want to start counting at x plus 1. Then r times fact y plus z minus fact y plus z minus 1 mod. Oh, actually, let's see. If y is greater than or equal to 2, then automatically we get all the permutations by the same reasoning. Otherwise, we use this formula. This formula that took me longer to explain than to derive, I guess. And something's not working. Because I didn't read in n. So I'm reading in absolutely nothing. Makes sense. 160540. It is under mod, it should be fine. Yeah, trust it. As always, penalties, whatever. Because I already started 10 minutes late, so it doesn't matter that much. Wait, is n bounded? Let's refresh my text editor. Why is it running so long? Time limit exceeded. I did not mean to do that. Is it the map? Okay, this is done once. You gotta be kidding me. Is it seriously the map that's that slow? Or is there something else? So again, factorial is being done once. So sorting using the map, taking that. If y is greater than or equal to 2, be done. I missed something up here. This is like an infinite loop or something. For I equals n, I is greater than y plus z. I minus minus. To do the infinite loop where it's the map, I'm going to test out the map theory first. I'm just going to naively count the elements. AI is equal to x plus r. So now I'll make these parentheses, and then I will call the function, and then I don't need to use the map. So I'm not really sure if that fixes anything. But I don't know how this would infinite loop, because the condition is being larger than something and it's going down. But also, like, map isn't that slow. It can't be that slow. Well, I don't know. Wrong answer on test 4. Okay. I don't know what's with that. But apparently that fixed it. Map was actually that slow. Somehow. I've not experienced that before. Oh, that's why. Because this isn't how you iterate through an array. My bad. Well, okay. So now something's wrong with this. Oh, that's why. Because it could be negative. Yep, that is also a thing to watch out for. In C++, the mod is as a note for myself. In C++, the mod is, like, it can be negative, and like a negative number mod something will still be negative, so you have to offset it by like adding mod or something, which is something I conveniently forgot about. So now you should work. There we go. There's a city that can be represented, any inversions? Okay, D is next. There's a city that can be represented as a square grid with corner points in 0, 0, and 10 to the 6th, 10 to the 6th. City has n vertical and m horizontal streets that go through the whole city. Sure. Okay. Borders of the city are streets as well. There are k persons staying on the streets, the pth person at a certain point. Yep. There's an inconvenient pair. They not have an explanation before? There's an inconvenient pair if the shortest path is strictly greater than the Manhattan distance between them. How would that happen? Okay, sure. That doesn't matter that much. Yeah, I'll do that. I do want those. When exactly does this happen? Let's look at this. 3 and 4. Oh, okay. So it's when they're between the same group of streets. Okay, so say I am 3. Say I'm 3 and I'm looking for the inconvenient pairs. If you're horizontal, I just go up to your street and then down your lane. So it's definitely Manhattan distance there. So vertical and horizontal doesn't match. It's only vertical and vertical that can match. And vertical like this would match with, if we match it with something that's not on the same like, sort of like bracket, like if we, okay, I can zoom out. That's cool. So there's something like on the same bracket. Like for example, say this is our street. Then I'm here. If you're like up here, then I can go up to some street that's below you, go horizontally to you, and then make that work. So really the only time where a pair could be inconvenient is when both of them are strictly between the same pair of streets. But I think that's it. Like, it at all. So also, if someone's on an intersection, they can never be inconvenient. They just go throughout. Yeah, I think this is the only case. Because otherwise, you can just take that path. Like, the direct path would exist if you're on an intersection or you're on the same, like you're both on vertical, you're both on horizontal. What? Oh, I did not mean to do that. Okay. So that should be it, and then we just code that. I guess the coding is the part that's kind of a pain. Because it doesn't have that many solves yet, but it doesn't seem that conceptually bad. Although I guess you can get stuck if you're thinking about other cases, like how else could you have an inconvenient pair? But I don't think it's that bad. So we're going to read in N, M, and K. Alright, we're using some useless arrays that don't make any sense in their variable names, but whatever. So, yeah. Another thing. I'm jotting down ideas for something I'm planning. That's why. So actually I'll put this here too. I do not need factorials anymore. I do not need factorials anymore, in case you didn't hear that because of whatever that was. And okay, so it was not the map that's the problem. And we have 2 seconds, so let's try that again. Actually, no, we don't need to. Okay, so let's start with vertical. So let's only consider the x coordinates of people. No, only consider the x coordinates. So we're going to try to find the people that are inconvenient, like via this and so on. Okay, good. It is between 0 and 10 to the 6th. I do like that they did that. That is nice. Okay, so let's do like pairs. And then up to 300,000. 300,000, not 30,000. So we're going to read into the pairs. So first we sort them by their x coordinates. In fact, we're going to do it twice. No, that doesn't. Let's just not. So we're going to sort them by their x coordinates. Now we're going to also keep a pointer to the current sort of x coordinate that's like we're in between. Or we're gonna keep a pointer to the largest x coordinate that's behind us, that's smaller than us. Count is equal to 0. So now for I equals 0, I up to k, I plus plus. So while point, we don't need that. Point is less than n, and p point dot first, the x coordinate is, no, this should be the next one. Well, p point plus 1 dot first, we're considering when this is smaller than this. So if we move from here to here, then we want to move from this one to this one. So this should be smaller than this, or less than or equal to make it work. So is less than or equal to, no, sorry. So the coordinate here, so a point plus 1 should be less than or equal to pi dot first. Right? Yeah. Alright. Point plus 1 is less than n, and a point plus 1 is less than or equal to this. Yeah, we're looking for the next one that like it becomes smaller than. So then we know that within this group there are a certain number of people, and they all form bad pairs with each other. So we're going to count the number of ways to choose 2 people from that, which is like if we have x people here, it's x choose 2, which is x times x minus 1 over 2. It's just a formula. So in this case, x is count. We're going to do that. Then we set count to 0. We reset it because we're in a new region, and plus plus point. Okay, so now now we need to consider, when do we start our new region? Like suppose we're here, for example, we're right here. Then this should not count for this because, again, anything on an intersection is fine. It will always form valid pairs. So we should only start counting to being within this region, sort of like exclusive region. We should only start counting when we do something. When we like are strictly within that region. So only if we're strictly greater than the coordinate at the pointer. So if pi dot f our person's x-coordinate is greater than a point, then and only then increase the count. Then we do it a final time. Okay, now what I'm going to do is I'm going to swap the coordinates so that the y positions now take the place of the x positions. Swap pi dot first. So now the coordinates are yx instead of xy. So I'll make that clear here. So here they're xy, but now they are yx. Also, just to make sure this is actually correct, like here we're doing x coordinates and these are x coordinates. We should be comparing x coordinates to x coordinates. So yeah, now we're doing yx, and the only reason is because I want y to be first so that I can sort by y. That's it. Then we're basically doing the exact same code. Remember this handles auto indent, which is nice. Yeah. So now we reset. We only have a few differences. This should be up to m. This should be this should be b. This should be b. I believe that is it, because now we're handling y coordinates, so we need to compare it to the y coordinates. Yeah, so we do this final part again, we add in the final group, then we print the answer. Let us attempt. 6. Okay. Why now? Why? Oh, that's why. Okay, I'm counting this pair, 6 and 7, when I shouldn't. So what I need to do now is I need to do this, the same thing. Okay, yeah, I realized this mistake. Glad that the sample was nice enough to do that, because I would have taken a lot to realize, I think. That they cannot be on the same y coordinate, for example. Because if they are, then it just sort of breaks everything. Like, of course, this can go to this within the Manhattan distance. So what I need to do now is, we counted all the pairs within this region, and we specifically need to subtract out pairs that are in the same y coordinate. So I'm going to keep track of everything. Let's see. So for, can I trust map iteration? I don't think I can trust map iteration. Because I remember in some old Div 3, that was the reason I lost first place, so I'm not going to mess with that again, for sure. Not going to mess with that again. Actually, we don't need to. Okay. Yes. Every time we insert something into the map, we subtract out the number of new pairs it makes by default. So instead of doing this all at the end, when I stick this coordinate in, I will subtract out the already existing pairs that it makes. So I'll subtract out this and I'll subtract out this. So really it just means subtract out whatever the count was before we had this element. So ants minus equals cur of this y coordinate, and plus cur that y coordinate. In fact, we can combine these two. I'm going to increment this right after we access it. I think it's a bit faster to do that, but I'm not really sure, and it doesn't really matter, because it'll just functionally work the same. So I will clear cur. Yeah, very glad the sample did that. That was nice. Not bad. What? Now we're at 4. Why are we at 4 now? That doesn't make sense. let's see which one I'm messing up. Oh, so then put that here. My bad. Is there anything else I added here? Any other copy paste errors? So we clear it in here, and we subtract it here, and do the same thing. There we go. Messing with the sound again. Hopefully it doesn't mess with the mic again. That'd be sweet. I mean, it shouldn't again, but I'm just really scared. Because I don't even know what I did before and I messed it up. Okay, screw penalty. Let's go. My goal as a screencaster is to finish this as quick as possible. Alright, we're good. So, I'm assuming my rank is actually like not the worst just because I'm actually solving things. Despite starting 10 minutes late, let's see how we'd be doing otherwise. I think it's like not that great. Could definitely have a better penalty, especially after all that stuff on C, those shenanigans. But whatever. That was just the byproduct of trying to write code too quickly, I guess. And the problem here was minus. Yeah, okay. So just like be more careful, I guess. That is what I should advise myself. I'm assuming F is harder than E? Yeah, so E has solves, let's try and do that one. Hashing. Okay. 2 of the K teams participate in a playoff tournament. The tournament consists of 2 of the K minus 1 games. They're held as follows. First of all, the teams are split into pairs. Yeah, so 1 plays 2, 3 plays 4. Odd n plays even n plus 1. Then you get rid of the, you kill the ones who lose, you do the same thing. Kill those, do the same thing. Until only 1 person is left alive. Sure, so tournament, yep. That's a different tournament from B. So after the tournament ends, B was the chess one, right? Yeah. So after the tournament ends, the teams are assigned places according to the tournament phase when they're eliminated. I'm just interested in the solve count. In particular, the winner gets place 1, the team eliminating the finals. Okay, sure. So it's 1 plus the number of people who did better than you. Yeah. Or rather, it's the number of people you played plus 1. Or like the size of the bracket you're in. After a tournament was just conducted, its rules were encoded in the following way. Let PI be the place of the ith team in the tournament. The hash value, K is 5. The hash value of the tournament is calculated as H equals sum from I equals 1 to 2 to the K of I times A to the PI modulo F of T num. Okay. Where A is some given integer. Well, I already have mod defined as that, so in case we do need to do that, I'll have that ready. FFT number right here. I keep calling it FFT. I should be calling it NTT, but I don't use either of them that much, so it doesn't. I don't know. I'm not like accustomed to it. But yeah, sure, NTT number. Unfortunately, due to system, like basically it's a mod that you can use. It's like a friendly mod, I'm pretty sure. Due to a system crash, almost all tournament-related data was lost. The only pieces of data that remains are the value of K, A, and H. All right. So I times A to the PI. I times A to the PI. I guess we have to abuse the tournament rules a bit. If we consider like 1 and 2, only one of them wins, the other just dies straight off. Okay, but somehow we have to find something that matches the hash. 2 to the k is 32. So, there are 31 games. Brute forcing that will not work. It is a sum, though. So it is possible to do something like meet in the middle. Maybe. Maybe. It's not that easy, though, because it sort of depends on previous results. Like, okay, suppose we brute force every game that happens before the finals. So, for example, I'm guessing it should be something like a meet in the middle problem. So, for example, we have, it does my university. That is weird. So we have these games, for example, like this. Then we have like the finals. And then maybe we have some more, like maybe we have something like this. I'll draw these out. So maybe suppose we brute force all of whatever's happening here. And we also brute force all of whatever's happening here. Right. So now we have a bunch of possibilities for that and a bunch of possibilities for that. Now the question is who wins this? This sort of complicates, whoa, that's not what I meant to do. I meant to do this. So let's, this is fun. So let's like assume, like who wins this is the question, right? Because that cannot be that cannot be part of the state here, nor can it be part of the state here. But I'm guessing what we can do is we can say, okay, we're going to brute force what happens here, and then we're going to explicitly say this person, the person here is going to win the finals. And then on the other side, we can say that this person is going to lose the finals. Then that way, within the meet in the middle, we can match the ways where one person wins and one person loses to each other, and we can try and match the hash. I'm guessing that is the way it works, because the only problem with meet in the middle is this finals part, like who wins. But we can say that one person will win and the other person will lose, and everything will be fine. So, alright. So, I'm gonna actually make this normal now. So this is, why am I red? So, suppose k equals 5, the worst case. Then this is a tournament of size 2 to the k minus 1. This is a tournament of size 2 to the k minus 1. Both are 16. So there are 15 games that happens. In each game, one person gets eliminated. So in total, there are 2 to the 15 potential outcomes that can happen if we brute force all of the potential outcomes in each side. Then we match them to each other, and I think it should work. Okay, so what I will do is, in terms of implementation, we have to restore the answer, of course. The problem makes no sense if you don't restore the answer. Well, actually, you could say yes, no problem, but like it's better to restore the answer because otherwise it's dumb. So, alright, so we print the places, which is awesome. So really, we could just straight up, we do like a map that says like the partial hash, I can spell, partial hash goes to a list of places. And then this should work, I'm pretty sure. Okay, so let's just do that. So, let's say LLA. I'll make it X. So, Cn to K to X and Y, I guess. be the hash. Because I already have this array here and I don't really want to mess with it. So n is equal to the k. Right, so if k is 1, there are 2 people. So that makes sense. Alright, so now map a long to a vector, I guess. Like meet in the middle, like meet, I don't know what they call it. Like possibilities. So first dimension, so these two things are like, the first is whether or actually I'll switch the order. The first is the side, so like is it the top or bottom, and the second is whether the representative from that group wins the finals. So let's do let's make this function called gen. So start is equal to p times n over 2. So if p is 0, we're going from 1 to 16. If p is 1, we're going from like 17 to 32, or rather n over 2. So m is equal to n over 2, because we're solving for a half. Now let's see. Right, okay. So to implement this, it's actually kind of annoying. Maybe. I guess it's not the worst. What we need to do is like, actually, yeah, sure. So we're doing over the mask. That should work. Right, then what we're going to do is we're going to compute like a running hash. And we're going to iterate over whether the last person wins finals or not, or the best, like the winner of this bracket. So let's go now for. Also, I didn't actually explain how meet in the middle works. I guess I'll do that when I actually code it. But basically, you compute 2 halves, then you combine their answers. So for I equals 0, what am I doing? I is less than m, I plus plus. Alright, so for I equals 0, I is less than m, I plus plus. The place place is going to be the record of what place each person got. So here, I'm going to initially say the vector spot is the current people that are in each position. So initially, like, initially there's like 1, 2, 3, and 4, for example. Then maybe 1 wins and maybe 4 wins. So now this is the vector's spot. So then the first 2 indices are what matters. So I'm going to fill spot spot.end and should begin with start. So for we're going to iterate over the bracket size now. Initially it is 2 to the k minus 1. So 1, 2 to the k minus 1. No, yeah, this should be m minus 1. This should be k minus 1, yeah? Actually, it could just be m. That makes more sense. Size is greater than 1, and then we divide it by 2 each time, because each time half the people get eliminated. I'm also going to keep a pointer. This represents the mask. So the reason I'm doing this is because the mask will just tell the outcome, like the ith bit in the mask will tell the outcome of the ith game. So I need to keep a pointer to whatever game we're at so that I can determine which outcome we need. So size is m, size is greater than 1, size divided by 2. I don't actually need to iterate this. This should be fine enough. Yeah. This one. So for I equals 0, I is less than size, I plus equals 2, plus equals 2 because we're going through each game like that. Like we're going through 2 people. So the result is we're getting the ith, we're getting the point bit, we're getting like the bit at the position point of mask. So we shift it like point times so that the bit at position point, like we'll shift it so that the bit at the position point is to the right, and then we end it with 1 so that we only get that bit. It's more better explained visually, but like you can try and work it out for yourself, or maybe I can explain it later, but not right now. So if res, let's say the first person wins, so place spot actually let's do it with 0. That's easier, and then I'll just add start to every index. So this is like the index of the person. So 0, if we're looking at the first half, 0 would correspond to 1. If we're looking at the second half, 0 would correspond to, for example, 5, or n over 2 plus 1. That way indexing is nice. Actually, I don't know. Maybe it's better to do it the other way. And then we'll just subtract start so that we can extract the index. So then this is the actual players. I guess that makes more sense. I don't know. Is equal to, anyway, we figured out the formula. It's the size of the bracket plus 1. Except we're not looking at the size of this bracket. We're looking at the size of the entire bracket, so we need to multiply it by 2. So place spot plus start is equal to 2 times size plus 1. Actually, wait, is it 2? Might actually not be. In here, wait, these guys get place 5. It might actually just be size plus 1. Could be wrong. Actually, yeah, that makes more sense. If there are 8 people, people should not get 9th. Yeah, okay. So it's half of that plus 1. Everyone ties for that position. We're also going to keep the hash. I'm also going to do like hows. I'm going to pre-compute the powers of x so that it's not involved in computation. I is less than or equal to 100. 100 is a gross overestimate. r is equal to r times x mod pounds I is equal to r. So h is equal to h plus, it is the index, so this should be spot I plus 1. So it's going to be the index times the powers of something. This is the place, so size plus 1. Yeah. I don't know why I'm switching tabs so much. Yeah. And then, so spot I is equal to spot I plus 1. So I'm going to overwrite it each time so that the new, like these are positioned 0 to 3 before, and now these are positioned 0 to 1, and we don't really care what's in the other spots. Doing this is fine because we're iterating from smaller to bigger. So by the time we get to like an index that we're going to overwrite, for example, here we'll overwrite index 1, but we've already processed that. So it doesn't matter as long as we do it in this order. You can like do it explicitly and make a new thing. I don't know. Just however you prefer. Anyway, this is the exact same code except actually this should not be spot I, it should be spot I over 2. It is like it's the number of tournaments that have been played at this level, not specifically I. So I over 2 would be 0, and then 1, and then 2, etc. Because we're iterating up by 2 each time. So this is just that, except now we set everything to I. Actually, first wins, so this should be spot I. Person in position I wins. So this is the loser. Their score is being added to the hash now. Okay. I think that's it. Now we've done that. So now we consider... Now we're left with the winner. So now what we're going to do is we're going to consider 2 cases. If they win the finals, we're going to create a duplicate. This is sort of just like a duplicate so within this scope, so that I don't actually want to modify this or this. I just want to like have these variables. By the way, this is just like a scoping trick. I can make it so these are within their own scope, and then they won't be part of this like block of code, or the rest of the code. So what I'm going to do now is say, so place spot 0 is equal to 1, and then h is equal to h plus spot 0 times pals 1. Mod. This should all be mod. There are no negatives here, so this should be fine. Then, so this is pause for side P, that is this, and whether this guy wins finals, in this case it is 1, and then I'm going to set it to H, that is the map part, is equal to, I want to get rid of that period. Sorry, this should be NH, not H. We're modifying the new hash. Is equal to N place. And this should be new place as well. So we're going to do the same thing, except now we're going to say they don't win finals. So here, their place is 2, and everything else is the same, except this should be 0. So now, yeah, so let's start. So we're going to iterate over the first guy wins finals. And then we're going to say let's see. So we're going to iterate over this map. So for a pair of long longs and vectors of long longs, and then this should be pos 0, and then wins. Then we're going to look at the target. So the target is the number. So we have x, we need y such that x plus y mod m is equal to h. Right, so really we want y is equal to h minus x mod m. So should be the hash, required hash is y minus x dot first, and then again, because we can have negatives, we want to add mod. But mathematically, like, this should be positive. It should always be within the range of 0 to m minus 1, but in C++ that's not the case. So here we're going to add mod to make it so that it has to be within that region. You can even add some huge multiple of mod. Like, the whole point is that it just has to be positive. Or non-negative. Yeah. So now we're going to say, if pos 1 not w, saying the other side where they don't win finals, I don't know why, just that condition makes no sense. Dot find targ is not equal to that dot end. There we're good. See x dot second pos 1 not w. Otherwise you print -1. Yeah. So this is just testing. If it works, I will reconfigure the output. I just want to make it work first. I doubt it will, because I just wrote this whole thing from scratch. And it doesn't even work because multitests. And I close the program, because I do that. I really hate the control Q is quit, because that in Notepad++, that was the old, where are you? Actually don't know. Code, there we go. Yeah, in Notepad++, that was comment. And this is very, very different. Luckily I save religiously, so should be fine in that sense. That was an error. The error is something in printing. Oh, that's fine. I can't move you? I don't get this map. I don't get why. I don't understand what this is. Like this, like hotbar, and why I can't mess with it. But okay, then I will move terminal here as well. Yeah, this should be targ. My bad. And then targ. This should not be targ. This should be the map itself. The other part should be the access. Seg fault. That's a good start. Okay, so let's see where we actually get to. Actually, we might as well just like write this code now. For lo z x.s, yeah, z for lo z pos 1 not w targ yeah z yeah. Alright, where do you seg fault? I'm assuming, of course, here. But why? Well, first of all, I'm not a touching point. That doesn't change the most, though. So let's see where we actually get to. Actually, we'll try a smaller case. Oh, 1, 0, 1. Oh, wait. Is it the problem in the meet in the middle? No. Okay. So here, well, it would be 0, 1, 0, 1. And then somehow we get the issue. Let's try printing X. I'm not sure what that would cause. Why would that be a seg fault? Is it because it's dying like internally and then it just doesn't say it until later? Why use 0? That's another problem. Why use 0? Because this should be a minus start. That would be why. One, 3, 3, 2. Oh, it actually worked. The hell? Okay. I will take that. That actually like got the right answer. That's not supposed to happen. It's not supposed to happen this early. I'm supposed to like spend a few minutes like just crying over sad bugs. But if that is what you want to give me, universe, then I will take this. In any case, let's just make sure this works. Print the stuff, find the target. Don't do that. Starting from size from M to 1. Then spot I plus 1 minus start, the index. Add that to the hash. Continue on. Same thing here. Say win finals, then that's fine. Make sure one more time it actually prints the right thing. Like no debug prints or anything. Alright, that was relatively smooth. That's so few salts. Wow. Well, actually, it is 30 minutes left. I will definitely have some more people beat me soon enough. Like this rank is pretty good, especially for starting 10 minutes late and clowning C, but that will not happen soon enough. Also, is there some way I could have avoided this? Like, I mean, this was stupid. I guess just being more careful. Probably being awake helps too. Like actually having some sleep. That's not that common, but meh. Alright, 29 minutes. I doubt this will happen, but we can read it. You're given a simple undirected graph with n vertices and is even. You're going to write a letter on each vertex. Path in the graph is called Hamiltonian if it's each vertex. Once the string is called palindromic, it reads the same from left to right and from right to left. A path in the graph is called palindromic. No, path in the graph is called Hamiltonian if it visits each vertex. Once the string is called palindromic. Yeah, okay. Yeah. Path in the graph is called palindromic if it's Hamiltonian and... Wait, what? Oh. Okay. Yes. Definitions, right. So string length then is good if each letter is one of the first k lowercase Latin letters. So 12 to 12 is too much. If you write the ith letter of the string on the ith vertex of the graph, there will exist a palindromic Hamiltonian path in the graph. Oh, factorial, I'm assuming, is too much? Yeah. Note that the path doesn't necessarily go through in that order. Count the number of good strings. Sounds fun. Sounds great. Sounds like a good problem. Sounds very, 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 very fun. Very fun. Very fun. How many strings are there actually to consider? Because we need strings where every character has an even occurrence. Because n is even, every character must have an even number of occurrences. So if any character doesn't, then that is not possible. So that is a lot of possibilities. If they give a complete graph, how much would that be? It would be a lot. I'm still like in shock that this works so smoothly. That they're actually like, there's just straight up weren't any bugs. It was just straight path from writing code to, well, like a single seg fault because of this, because of inconsistencies, but other than that, man, that was great. So do I have any chance of actually doing this? There could be like a lot of Hamiltonian paths, is the thing. Checking if there is a Hamiltonian path is not that hard. We can do DP, but 12. 12 is like small enough that some things will work, but not like that many things. So you kind of gotta be careful with that. How exactly do we be careful? Well, as this shows, there are a lot of possible answers. 12 to the 12th is huge. It's definitely not going to work to iterate over the possible strings because there are like a lot of possible strings, even though there's the constraint that you need an even number of each amount of characters. So it's going to have to be actual counting somehow. 2 to the 24th is allowed. The problem is overcounting. If we had some constraint, like each letter can only appear at most twice, then that would be a lot easier, but of course that would get rid of the combo part, so. Exist a palindromic Hamiltonian path in the graph. How many people saw this? Yeah, I think there's a decent chance that we're fine as is. I have the worst penalty of anyone with. That's funny. What was C? C was the combo one. That was kind of annoying. Geothermal, holy crap, wins by such a large margin. Well, the second guy goes backwards, so I guess that makes sense. How are some friends doing? Not the best positives. Yeah, not the best. Sort of unfortunate. Though there are not many people doing it anyway. How many registrants were there? 25k, wow. Alright, well I kinda don't want to do this, because it's like, even if I do find a solution, implementing it's gonna be impossible. And I do have the feeling that it is combo, which I'm currently very bad at. Alright, definitely involves combo, it's counting. think I would just leave it and watch my place go down slowly as more and more people solve E. What happened with B again? Why is that so slow? Alright, that one was just like one of those problems. Okay, anyway. Yeah, okay, I think I'm satisfied as is. Watch that go up once again. Okay, so I'll do solutions for the ones I did. I guess maybe there's a chance I'll be above rank 69th, so I can put in the title, but I don't really know. Coming like 8 to 9 minutes late was also not helpful, but whatever. Okay, let's do this. I'm gonna move you here too. I really don't like that control and command, like command has a different function than control. Like command is like basically the Windows version of control for everything but a few certain things. Like control is zooming, for example. I have to like physically remind myself that they're not the same key, which is painful. But I guess that is how it is. So you have a string consisting of n letters. Each letter is either A or B. String is called balanced if you have the same number of A's and B's. So find any non-empty balanced substring, and then print the left and the right indices that contain that substring. So the thing is, n is 50. T is 1,000. Let's just look this up really quick. 1,000 times 50 cubed is passable. There are 2 seconds here. I think every problem is 2 seconds. But it's passable. There are every problem except for special ones. But it'll work. So, really, like, basically any algorithm that's not like, that's like decently polynomial will be fine. So literally, iterating over the first index, iterating over the second index, and then naively counting the number of A's and B's in each character will work. Because, or in each substring will work because the constraints are smaller. But there is an elegant solution that would work very easily for n up to 100,000. And it does not involve prefix sums. In fact, all it says is, let's consider the string. Suppose you have all A's. Then the answer is no, because you don't have any B's. Of course, there's no balanced substring. Suppose you have all B's. Same thing, the answer is no. Otherwise, you have some of each. So for example, suppose you have like A, B, A, B, B, A. Now, there will be a point where you have a string of length 2 where one string is A and one is B. Because like, you have an A, you have a B, they have to be next to each other at some point. Like, suppose they weren't, then what would you do? How would you have that string happen? Like there just has to be a point where there's an A and a B next to each other. Because if not, those two strings just have to be separate. I guess I can prove it, like just try and imagine a string where you have B's and A's but not together. So like, say the first character is B, then the next character is B, and then like what? When do you get an A? Whenever you get an A, then you have this instance of a B and A next to each other. So I don't know, I'm taking too much time on this, but that's the idea. That there will always be some string of length 2, substring of length 2, where there's an A and a B next to each other. And when that's the case, that string is valid, because there's one A, one B, it's balanced, it's even, everything's good. So really you can just look at every adjacent pair of characters. If you find anything that is different, if you find any pair of different characters, then that is the answer. Otherwise, you can be guaranteed that there's nothing, because it means that there has to be either all A's or all B's, in which case there's no answer. So just look at every substring of length 2, basically. So code, I just do that. Go through each pair. If it's not equal, print that. Otherwise, there's no answer. Yeah. Next part is chess tournament. So, essentially the way this problem works is, I think I'll refrain from reading problems. But like you have people who are playing in a tournament, I guess, and certain people have certain expectations. So the tournament pits everyone against each other. Every person will play every other player, and there are two types of people. Some people don't want to lose anything, so they will be very sad if they lose at least one game, and other people just want a single win, or they want to win at least one game. You want to figure out if it's possible to, you can sort of rig the matches. You can decide who wins, who loses, or if they draw. And so you want to rig the matches so that every player is happy. They get what they want. So type 2 wins at least once, type 1 doesn't lose. But they can draw. So let's look at some configurations. Suppose you have all 1s, like just all type 1. Then everyone can just draw each other, and that would work. Because nobody loses, everyone just draws. So in this case, you can have everyone draw. What if you have something like, now let's look at the amount of 2s. Like sometimes that's impossible. Like for example, suppose you have exactly 1, 2. Well, the 2 wants to win, but all of these people don't want to lose. So who can the 2 beat? As it turns out, it's nobody, right? Because they have nobody to beat. Everyone else can't lose. So, in general, let cx equal number of x. So if c2 is equal to 1, then the answer is no. What if you have 2 2s? Then you can do something like 2 2 1 1, and c2 is equal to 2. Well then, again, these 1s are irrelevant because you cannot beat them. So, they can't lose a game. So really, the only game that matters is when these two guys play each other. But only one of them can win. The other will lose, and the other will not win any game because they lose against the one person they're against. So yeah, that just doesn't work. So in c2 equals 2, the answer is also no, because one player will always lose. I'm trying to remember some specific thing that had to do with tournaments. Right, okay. And these are the only special cases, because we can develop a strategy that works for everything else. So when c2 is greater than equal to 2, greater than equal to 3, the answer is yes. And the way we work is, let's suppose this guy has to win a game, of course. So let's say we'll have him win against the first 2, against the next 2. And then this guy can win against the next 2. And then this guy can win against the first person that was a 2. And so we can sort of make a circle out of them, and we can do this with like any amount of 2s. And the reason we couldn't do this before is with 1 there was nobody to beat, and with 2 we couldn't go back because going back would mean that we faced the same person that we just lost against. But for the rest of them we can do this. We just make a line out of them, and everything works out perfectly. And then we can say that every other game is a draw, so that 2s will only win against 2s, and 1s will draw against everyone, so that no one will lose against another one. So these are the wins, and the rest are draws. So really this is how this strategy would work. If everything is a 1, so we're going to count the number of 2s first of all. So if c2 is equal to 0, if everything's a 1, then we just make everything a draw. In fact, we can make everything a draw by default, and then we can just set some of them to be wins to satisfy the 2s. So if c2 is, if the number of 2s is 1 or 2, answer is no. Otherwise, if it's more than that, we again initialize everything to be a draw, then we make this sort of cycle between the 2s. And then we say certain people are going to win against certain people, and then the rest are going to be draws. So yeah, this is fine. This works because it satisfies the conditions. The ones don't lose against anyone, and the twos beat each other. Or the twos win against at least one other person. Win against at least one other person. So let's now... I think that's it. That should be the only caveat. In terms of implementing this, so first of all, I'm using a list of an array of strings just because strings are arrays of characters, so that handles everything. So I'm creating like a count array first. Then I'm counting the number of 1s and 2s. Subtracting the digit 0 means that the digit 1 gets converted to 1, the digit 2 gets converted to the number 2. So now count 1 and count 2 tell me the number of 1s and 2s. So now, for each thing, initially everything will be a draw, and then I set the guys who play themselves to be X because that's what the problem says to do. Now, for the number of 2s being 1 or 2, it is immediately impossible. Otherwise, if it's 0, we already have everything as a draw, so we don't need to do anything. So we only need to do anything if there's at least 3. So what I'm doing is I'm keeping track of the indices. So for example, say I had the string like 1, 1, 2, 1, 2, 2, 1, 2. Then the indices here would be 0, 1, 2, 3, 4, 5, 6, 7. And the indices of the 2s specifically would be 2, 4, 5, and 7. And so I can say 2 beats 4, 4 beats 5, 5 beats 7, 7 beats 2. And then, so yeah, I'm creating this list of indices. And then I'm getting like the next index, which normally is that index plus 1, but for here it needs to overflow. So if this is initially index m minus 1, then plus 1 we add to n. Then we can do like the index mod n, and then it would become 0. It's sort of like a trick for like circular arrays that we do at modulo n. You can also just say like at the end, treat it like a special case and just make it 0. Either way is fine. And then I'm setting that person to win and the other person to lose. Then we print stuff. Printing a string is just printing a string. That's why I made it, did not mean to do that. I like that Chrome gives you a second check, because sometimes I hit Control W, which closes the tab, and sometimes I miss and hit Control Q. But it always gives me that warning, which is nice. There are some things that are nice about the Mac, I guess. Not everything, though. Next part, we are counting certain permutations. So we have a list of people. Each person, essentially we're going to go through these, each person has a number. We're going to go through these people in order. So say we have like 2, 3, 1, 4. This is our order. So we can reorder these people however we want. So like for example, 2, 3, 4, 1. I can do that. And then we're going to go through the process. And the process is saying we're going to go through the people in order. And if they, if they have like a number that's positive, then they will reduce 1 from their number and they'll like shout something. So this guy becomes 1, this becomes 2, this becomes 3, this becomes 0. So now the people that will shout here are this, this, and this. And this guy does not shout because he doesn't have a number anymore. Now this guy doesn't shout as well. So now this guy will shout once again, this guy will shout once again. Now he's the only person left that shouts, so that's happening. That is the process. We call an ordering bad if someone shouts at least twice in a row. So for example, this ordering would be bad because the 4 shouted twice in a row. Because at the end, the final configuration before he shouted again was 0, 0, 2, and 0. So he would just shout twice in a row because he's the only one left with positive numbers. So this is bad. We're given the list of people and their numbers. We can reorder the people however we want, and we want to count the number of orderings that are not bad. We want to count the number of orderings that are good so that no person shouts twice in a row or more. Right. So first, to approach this problem, we want to figure out like what does it exactly mean to shout twice in a row? Like, in what instances would this happen? And then we can try and count those instances. So let's, for example, say that like we have 4 as our biggest number. Or maybe I'll use 5, because that was what I used when explaining before. So we have 5 as our biggest number. Say we have something like 2. Then no matter what we do, this guy will shout twice, this guy will shout twice. It'll be 3, and then it'll be 0. So the 2 will not interfere at all. The 2 doesn't have a significance, because this guy is much bigger than this guy. Suppose we have a 3, it has the same effect. He'll have 2, he'll have 0, he'll still shout twice in a row. If we're here, we'll have 0, we'll have 3, he'll shout 3 times in a row. So what are the ones that matter? Well, if we have a bigger element, then this guy will run out of moves, will run out of his number before this guy does. So this guy is sort of obsolete. So really we only care about the largest number in the array. So suppose the largest number again is 5. Then say we have like another 5. Well, then these guys will go like this. They'll each shout 4 times respectively, and then they'll have 0, and then they'll both have 0. So if you have like multiple of the same element, multiple of largest elements, if you have multiple largest elements, then it turns out they are all good. And the reason is because these two will always sort of like counteract each other. This guy will always be alive when this guy is, except for the final turn, but the final turn is fine because then they won't shout twice in a row. So if we have multiple largest elements, we're all good. Now we assume the largest element is unique. So now we're solving the rest of the problem, so we're saying we have a unique largest element. So we've concluded that anything less than or equal to 3 it has no effect. In particular, say the largest element is x, then anything less than or equal to x minus 2 will be nothing. So we already know we have unique largest numbers, so we don't have any more x. So the only number that leaves us to consider is x minus 1. So in the spirit of this example, let's look at 4s. What happens with 4? This guy will shout 3 times. This guy will shout 3 times. So then 1, 1, 1, 0, 0, 0. That works, doesn't it? Well, what about the other side? 4, 5. So they'll shout 3 times each. 1, 2. Now he will shout, there will be 0. And then now we have this 2 here. And oh no. Right? Because now he has 2, everyone else is 0, so he shouts twice in a row. And that's really bad. That shouldn't happen. So the ordering of the next smallest element matters. If it's on the right, everything works out. If it's on the left, it doesn't. And it also, like, it's fine to consider every pair of elements uniquely, because we only need at most one element to get in the way of the 5 shouting twice. So we can consider each pair sort of independently. As long as at least one person gets in the way, then we're fine. So now, what do? Well, what we do is we check the audio and hope that it's still working. And it seems like it is. If I tap the mic, it's fine. Yeah. I'm sorry about the fan, by the way. Like, I can't do anything if it's not on. Seriously, it's really not great in here. Yeah, so that's why we're asked to count permutations, because the order does actually matter. We're asked to count the number of permutations, or the number of orderings of the people. I can't find one though. The number of orderings of the people so that it works. So what is a bad ordering? Well, we conclude that an ordering is good when, if the largest element is x, then x minus 1 is after. So if any instance of x minus 1 is after, then we're fine. So the bad case must be when the x minus 1s are before. If every x minus 1 is before, then that doesn't work. Yeah. So if every x minus 1 is before, then it just doesn't work. Another case is when we don't have any x minus 1 at all. Like suppose our array is just 5, 3. Then automatically we lose. So if we don't have any x minus 1, then it doesn't work. So really now, within the total, within all of the possible orderings of all of the numbers, we're sort of isolating just the instances of x minus 1 and x. Suppose we have k, the count of x minus 1 is equal to k. Then what we need to do is we need x to be we need x to not be last in this sort of subpermutation. If x is after all of the x minus 1s, then it's a bad permutation, and otherwise it is not. So how many permutations are there where x is last? Well, x can really be in any position, and it has an equal number of ways to be in any position. So there are k plus 1 positions. There are k plus 1 positions because we have all these x minus 1s and we also have x. So there are k plus 1 positions. And there are k positions that work for x. It just needs to be anything that isn't the last. So it follows that the ratio of permutations that work is k over k plus 1. Because as long as the permutation has x not being last in this relative ordering, then it is fine. And otherwise it is not fine. So the answer then is the total number of permutations times this ratio of permutations that work. And again, we ignore all the other elements. So the answer is n factorial times this. There are other ways to get to this answer. My code does it a bit differently to avoid division because I'm lazy. But the easiest way to do it is to just do it like this. Find the ratio that works. Another way is saying you're placing for the rest of the elements, once you place these down, you're placing k plus 2, k plus 3, ... up to n. And then this is the number of ways to permute n minus k minus 2 numbers. Or rather n minus k plus 2 numbers. Yeah, it's the number of ways to permute n minus k plus 2 numbers, so it's really np n minus k plus 2. And then that will be multiplied by the number of ways to make this permutation work, which is k times k plus 1, k over k plus 1 times k plus 1 factorial. And the reasoning is because we're considering these permutations independently, and this ratio still stands, that of these permutations, only that ratio of them works, because any permutation where x is last is bad. So this is another way to think about it. My code takes that approach, and then it converts this to an integer. This is k plus 1 factorial minus k factorial. Or rather, which is equal to k times k factorial as well. That's the thing. And you get this because k plus 1 is equal to k plus 1 times k factorial, and then you make that you take that ratio in, and then you get k. I'm just over explaining stuff. Anyway, So this is like the final answer. You can get to it in multiple ways. I think this is probably the easiest to code. You just do it, and then you're done. So you also, again, you have to consider the casework. And this formula also works when when k equals 0. Because when k equals 0, nothing is valid. Because then the 5 is too big. All you have are 3's or less. You don't have any 4's. So when k equals 0, then the answer will be 0, of course, because you have 0 on top. So everything works out pretty well. So we first consider the special case of if we have multiple largest elements, then everything is good. And otherwise, we have a unique largest element, and this is the answer. K being the number of instances of the largest element minus 1. So I initially used the map, and then I created this count function just because I was concerned about map, even though I got time limit exceeded, but it was from a different issue. So here we read in n, we read in the array, we sort it because it doesn't matter. We're counting orderings anyway, so it doesn't matter if our internal processing uses a different order. Because any ordering will still be equivalent. Okay, so we're counting the instances of the last element. If it's more than 1, immediately it's n factorial. Every permutation works. Otherwise, and we're also counting the number of that element minus 1. Then I'm computing, that loop is computing this, and then it's sort of a different way. You can do out the math. I don't recommend following this code, but you can do out the math if you want and show that it's like equivalent. And then the final part is we multiply it by specifically this formula. So you can also use this one. Either works. In fact, I should have used the other one because I got a wrong answer from the minus, because C++ modding can go negative. I will elaborate on that soon in a different video. But if you mod like a negative number by something, it might stay negative, which is not what you would expect mathematically. Okay, this next one, I guess it's like an educational problem, so sure. It was just kind of like there. It doesn't really like do much, it's just kind of a problem that exists to fill in the gap between C and E, I guess. So when is a pair inconvenient? Let's think about the possible cases. Let's just think of it like this. I guess the hardest part is doing the casework for when the pairs are inconvenient. So let's look at someone on an intersection. Anyone on an intersection will never be inconvenient with anyone. Because no matter where anyone else is, suppose they're like suppose they're only on a horizontal street. Then I can go down vertically to their street and then do that and not have any issues. Suppose they're only on a vertical street. Then I go left or right and then down. Or I go horizontally and then vertically. Or you can go vertically and horizontally to meet someone here. So if you're on an intersection, you're fine. So we're only going to consider people that aren't on intersections there. So let's consider someone like this. Someone on a horizontal street. Then maybe there's someone else like down here on the vertical street. But anyone who's only on a vertical street, again, is always going to be possible. And the reasoning is because we can move horizontally to whatever their street is, and then we can move down, or up, like we can move vertically. And that will be optimal. It will be exactly equal to the Manhattan distance, because we can always just go the horizontal part first and then the vertical. And if we consider the other way, we have someone on a vertical street, and we're considering horizontals, we do the same thing. We move vertically first, and then we move horizontally, and everything would work. So now the only case is when someone is in the same orientation. We're considering someone on a vertical street with someone else on a vertical street. This is when it is bad. Because you sort of have to, like, the optimal path would be somewhere in this rectangle. It would be going through some path in this rectangle. But that doesn't work. And it doesn't work because how would you go through this rectangle? It's just not possible. In other cases, for example, when you're on an intersection, this rectangle can like cover the whole screen, or it can cover everything. And like horizontal, vertical, for example, you can sort of make the rectangle like here, and the rectangle aligns with one of the sides, just because it does. But here, it does nothing. So we have to go around, either this way or this way. It actually doesn't matter. But the point is, we'll take some extra distance. That's not the Manhattan distance. So these are inconvenient. So people on the same... But what about other instances of vertical? For example, let's consider like this. Well, if it's like this, then we can make it work. Because we can go to the street in between them, move vertically, and then go like that way. And in the horizontal case, like horizontal and vertical are basically equivalent. Dimensions kind of like don't matter here. X and Y are the same. So we just go down to some street in between them, move horizontally to get to their level, and then go down. Or go vertically again. So now it goes to say the only case that's actually bad is when they're in the same sort of group of like street. When there is no vertical street between them. There's also another catch that I didn't think of initially, that of course they can't be on the same level, because then they can just go directly towards each other. Huh, I can title the page? Okay, that's kind of cool. And I can title it however much I want. Cool. Anyway, so yeah, like these guys are the only bad pair. These guys are not a bad pair because they're right next to each other. Alright, so how do we count this? Well, suppose for this street group, we have a list of all the people that are on this street. So we can count the number of pairs of people on this street by saying like, here we have 6. The number of ways to pick a pair is 6 choose 2, which is 6 times 6 minus 1 over 2, which is 15. So in general, if we have x people, we have x times x minus 1 over 2. But we also have to discount the people who are on the same level. So really we're counting all the pairs except the pairs of people that are on the same level. But we can count the pairs of people that are on the same level. It's like the number of ways to select a pair from this level. So say we have k people here, then we subtract out k choose 2. Or k times k minus 1 over 2, the number of ways to pick 2 pairs. And this is the same thing. We subtract out that, and we subtract out that, even though it doesn't actually subtract anything. So we count the number of pairs for each person in the same group, or for each, like... We count the number of pairs for each group of streets. And we also discount the number of pairs in the same group of streets that are on the same, like, vertical or horizontal level, because we don't want to count that. So that's sort of our strategy. And the way we sort of group together people on the same like vertical or horizontal street is a lot of ways work. You can do like binary search to find the nearest lower street, and then you can do it like that. You can do what am I saying? You can do other things like I use 2 pointers, which is fine. And then it just sort of groups people together. And then when you move onto a new street, you sort of like reset the state and you get rid of everyone in your current street. That would be how 2 pointers works. So I'll just show my code for 2 pointers. We read in all the input. Initially these points are x comma y, and then eventually I'll make them y comma x and process them the exact same way, because again x and y are sort of the same. They're sort of equivalent in how you handle them. So you sort by x. These are already sorted, which is convenient. It does mention that explicitly, that these are like in order. And the first one is 0 and the last one is 10 to the 6th. So everything's within the bounds, which is also nice. Right, so what are we going to do? We're going to iterate through the people, and we're going to say Again, we're keeping a pointer to the smallest. Draw a sloppy box this time. We're keeping a pointer to the largest vertical street. I'll only consider like the x coordinates. The y coordinates are the exact same. You just like swap the coordinates and everything works. So we're looking for the largest street that has a coordinate less than or equal to our current point. So when we move over, this largest street moves over to here, and so on. So we're processing the people in increasing order of x. So example, we start off here. Then when we encounter a new person, if they're in the same street as us, we add them to the count of people that are on this street. And if they're not, then what we do is, now we need to count the pairs. So now we're going to count all the pairs of the people that were on this street, and then we can do it like that. Another way, and I think this is actually easier, is when you add in a person, you immediately add in the pairs that it gains, like the number of people that were already on the street level. And then you also subtract out the pairs that you don't actually want to count, which is the number of people that were on the same level as you. So you can do it sort of dynamically, where every time you add in a person, you add and subtract the number of pairs it creates. And then when you reset this, all you need to do is reset the counts. I sort of did a mix because I'm weird. I did a mix of like dynamic and not. So what I did was, when I added in a new person, I discount the number of pairs on the same level. So I do the subtraction part, but not the addition part. I only do the addition part when I get to a new street or when I hit the end of the array of people. So when you get to a new street, then and only then do you count the pairs from the people that were on the previous level of streets, which is again that choose 2. And then, yeah, same for y. I use the map to just count the x coordinates. You can like use not a map, but it doesn't matter. Yeah, so do 2 pointers. If the thing changes, if the like current highest less street changes, then add to the answer that, clear the map so that everything resets, clear the people, and then increase the pointer. And this condition is necessary because, again, if someone's on an intersection, then it just like like there are no bad pairs with them, as I showed earlier. So if someone is on some x coordinate and they're also on the if they're on the x coordinate exactly of a street, we know they're already on the y coordinate of a street because we're iterating through that. So the x coordinate is also perfectly on a street. Then there's nothing we can do about this. Yeah. Actually, maybe they're not on an intersection, but maybe they're here. And again, because we're considering only the pairs of people that are on, they're on like horizontal segments of street, the people who are on vertical segments of street don't matter because we already know that they can't form a pair with us. So anyone exactly on a vertical segment doesn't matter. So we only consider the people that are not on vertical segments, and therefore we know that they're on the horizontal segment because they have to be on at least one. Right, so we do the same, so we do that, and then at the end I add the count. Then I swap the coordinates so that so that the first coordinate is y, and that's just so I can sort by that. There's no other reason. I just want to sort by y. Then reset everything, do the exact same code pretty much, but swap n and n and swap the first away with the second, and then answer. Yeah, again, you would group people together by their other coordinate so that you discount the pairs that you don't want. Alright, we're almost through. I didn't do F, barely even tried it, so I leave you at E. I recommend parsing the statement for yourself. It is generally a good idea to read statements like this because they're kind of long and it's good to be able to understand stuff like this. Now I guess like you're playing a tournament, people have ranks. The tournament was hashed. You want to find a tournament that matches the hash. So k is 5. That is important. K is 5, which means 2 to the k is equal to 32. 2 to the 32 is equal to around 4 billion, which is too much to process in code, especially with a lot of overhead from doing extra operations. But we don't have to do 2 to the 32. Let's imagine like some tournament that happens. Like this. Then this happens. Can I copy? How easy is it to copy? It is very easy to copy. Awesome. Okay. So then we do the same thing here. So let's consider what effect each group has on the hash. The people who lose here are just sort of they're sort of doing their own thing. The person who loses here doesn't affect anything outside of here. And same for this. The people who lose like within this bracket don't affect anything outside of this bracket. So really the only person that matters outside of a bracket is the winner. Everyone else, like if we sort of fix the stuff that goes on in the bracket, everything else can be summed up within the hash. The only other thing we need to keep track of is whoever the winner is, so that we can figure out what happens later on. So what if we try to exploit that? A common technique when like the input is pretty small, but it's too large to do like some 2 to the n or exponential thing, is to split it in half. An O of 2 to the k over 2 algorithm would work. And in fact it does, because that's my solution. But an O of 2 to the k over 2 algorithm does work. But how do we do it in O of 2 to the k over 2? With some extra factors, like O of k or something. But here, what we're going to do is, we're going to compute stuff for half the tournament, here, and also here. We're going to do stuff for half the tournament. And why does this help? Because again, we're going to do like each half of the tournament by itself, and then we're going to sort of combine them at the end. And the reason this is nice is because, again, the only person that matters coming out of the tournament, like the only information we need to store is the hash for that part of it and the winner. And again, the hash and the winner. So suppose we do that, then there are a lot of different ways to handle it. Yeah, we can like, for example, look at pairs of winners, and then we can say person X has to win from here, person Y has to win from here. And then suppose X wins the whole tournament, then we just need to find a pair of hashes that combined with like whatever hash like Z you get from here is equal to like the target hash. So you can look at all the possible results from one side, and then you can match them to a result that works from the other side. And if there's no match, then there's no result that works, because yeah. I don't know if I'm explaining meet in the middle that elaborately, but basically like what we're going to do is we're basically computing all possible results for this. There are 2 to the k over 2 minus 1 games that happen within this half of the bracket. And same for here. Because there are k over 2 people, all but one need to be eliminated. So there are that many games, and we can basically just brute force. We can brute force who wins each game and all the possibilities for people winning each game. So that is something we can do. And for each pair, for each thing, we extract a pair of the hash and the winner. Although I did do it a bit differently. What I said was, instead of explicitly storing the winner, I stored instead a flag. Instead I stored like a flag. And what this flag said was, I basically said beforehand who is going to win the final match. Because if we know who wins the final match, like suppose the player from here will always win the final match, then we don't care about this person anymore, because now we know what they contribute to the hash. We know that their place is going to be 1, and so all we need to store here is the hash. And same for here, we know this final person's place is going to be 2, so we know what they contribute to the hash, then all we need is the hash. Then we're reducing it to the problem where we have 2 arrays, we need to find a pair of numbers that sum to a specific number. You can do that with like a map or something like that. That's a very common problem. Like 2-sum, I think. Yeah. It's gonna be done in linear, logarithmic, or linear-arithmic time. It's like pretty fast. Anyway, that's not the hard part. So we can't exactly say that this person's always going to win the finals, but we can say that like we're going to compute the hash assuming that this person does win the final, and then we can compute the hash, and then we can also compute the hash assuming it doesn't win the final. It's only like a single change each time. It's just whatever this guy contributes. We do the same for this. And then when we're trying to find a pair of hashes that works, we only match hashes. So if we say this guy is going to win the finals, then we only look for matches where this guy doesn't win the finals. And if we say this guy doesn't win, then we're saying that we're looking for matches where this guy does win. So we match opposite flags. And as long as the flags are opposite, again, all we need are pairs, is a pair of numbers where the 2 things sum to a specific number. It's also modulo, but that's fine. So suppose, and the way we do it is we iterate over the number from the first group, and then we find out the exact number we would need from the second group to get the desired sum, and then we see if that number exists in the second group. And if it does, then that's our answer. So we're iterating over the first group. We just need to find the number that would work for us, and then we see if that exists. So for example, let's say you know x, and you want x plus y mod m is equal to z. This is not that hard to solve for. You know x, and you know z, so really you want y is equal to z minus x mod m. Note that mathematically this is defined to be greater than or equal to 0. In C++, that is not always the case. Sometimes you might have to add mod once, so that the subtraction is counteracted by the adding of the mod, and thus the number will always come out to be positive. That is sometimes necessary. And it's fine to do that. Yeah, so we're going to, in brief, we're going to generate all the possibilities for what can happen from this tournament, including the possibilities for whether the winner of this bracket wins the finals or if they don't. We're going to do the same thing. What the hell? We're going to do the same thing for the bottom side. And then we need to match them together so that they create the final hash that we want. I swallowed something from the air. That's fun. You see, you had a fan blowing around dust all the time. Yeah, so that's kind of cool. If I move the pen down here, it'll detect that I want to draw, and otherwise it'll use like the mouse. That's actually pretty cool. Right, okay, so what we want to do is we're going to iterate over the pair of the hash and whether this person won the finals. Then we know we have a specific x and we have a specific target value z, so we compute y. We compute y being the hash that we need from this group. then we look in some sort of map, for example, like hash map or just a set or something, some data structure that allows lookup. And then we look for the pair where the hash is y and the flag is whatever the opposite of this flag is, because both of them can't win the finals and one of them has to. So if this guy loses, the other guy has to win. If this guy wins, the other guy has to lose. So we look for the pair of y and opposite in the map that we're using. If we ever find that, then that is our answer. So the map on both sides will store the hash and the flag. And then it will map those to the list of ranks. Like the positions that each person had. What do they call them? Places, I guess. Yeah. List of ranks, places, scores, or positions, whatever. And then this will be for the half. And then when we match them, we'll take the list of ranks from the first half, we'll take the list of ranks from the second half that we know, and then that's our answer. So that's meet in the middle. And it'll work in 2 to the k over 2 because the bulk of it is enumerating all possibilities for each half. So what I'm going to do is read an input. I'm going to pre-compute powers of A just because I didn't even go over the hash function, but it doesn't really matter. I'm going to pre-compute the powers of A so that it's like fast. Yeah, meet in the middle is the tag. And then we're going to compute n, which is the number of people in the tournament, as 2 to the k. This is a 1-bit shifted a certain amount of positions to the right. Each shift multiplies it by 2, so shifting it k times is 2 to the k. Then I will generate for the first half and generate for the second half. I'll go over this code after. But once we do generate, we're going to iterate over whether the first person wins the finals. Then for each possible outcome for the first player winning the finals and like the hash, the first number is the hash, the second is the list of positions. We find the target. Again, you have to add mod to keep it positive or keep it non-negative. And then we ask, does this exist in the map for the other half? In particular, does it exist where the outcome for the second player is it's the opposite of the first guy. So if the first guy wins finals, the second guy doesn't, and vice versa. If that's the case, if we find that matching, we print both sides, because again, we're automatically storing the list of ranks, and then that's it. So this whole thing works in like O of 2 to the k over 2 times the complexity of the map. So it's like 2 to the 16th, which is, it's like 60,000 something, it's not that bad. And yeah, and it's like plus a log factor or something for the map, but that's also not that big a deal. Actually, it's a bit more because storing maps of vectors is kind of a pain, but it's not that bad. So then, to generate, I'm iterating over the mask of things that happens. And this mask is simply like, I'm going to go through the games in order. I'm going to consider like, first what happens in this game, then what happens in this game, then what happens in this game. And then this mask is just going to tell us in order what happens in each game. If it's 0, the first person will lose. If it's 1, the first person will win. Like, if that bit is 0 or 1 in the mask. So we just need to maintain like the current position in the mask we're at, so that we're making sure that every position in the mask corresponds to a game. And every game corresponds to position in the mask. Implementation-wise, there are a lot of ways you can do this. What I'm doing here is I'm keeping track of the current people that are still like in the game. So for example, suppose you have 1, 2, and 3, and 4. Like this would be the current list. And then when you win, then this person, like say 1 wins and 4 wins. Then I'm going to put 1 in whatever the first position is, and I'm going to put 4 in whatever the second position is, and this is the new array. If 2 wins, I would replace this with 2, And then if 3 wins, I replace it with 3, and so on. And then this is the new array, and we handle it in the exact same way. It's fine to overwrite because when we get to this position, we're already done with all these, so we can overwrite stuff that comes before it. You can do it without like overwriting. You can be smarter about it, but it doesn't matter. Like it works either way. So for each like number of people left up until you have 1 person left, then for each game, we find the outcome of the game, then we increase the pointer. This will just shift it point bits to the right, so that the bit that's like index point will become the bit with index 0. And then we end it with 1 so that we only get that bit. Like it extracts the bit in position 0. And everything else will become 0 because it's being ANDed with 0. You can sort of like write out like all the bitwise numbers, including like leading zeros and stuff like that, and it'll make more sense. And probably there's some like bitwise tutorial that explains how to get like it's just getting a specific bit of a number. So if the first wins, then we're going to say the position of this person is whatever it is. You can do some math to work it out. Turns out to be the number of people in this half bracket plus 1. So it's like the number of people in the total bracket divided by 2 plus 1. So it's the same value. Then add that to the current hash of this configuration, and then say that the other person is the new winner. And otherwise, the other outcome happens, we do the exact opposite. Now, after all this, the winner is in the first position of this list. So now we go over 2 things. We say they win finals, or we say they don't win finals. This is sort of like a trick, like you have like if statements and they have like brackets and stuff. This basically says like, this will be created within the scope of only these brackets. So this variable doesn't exist outside of the brackets, which is nice because then I can redeclare and I can copy paste the same code without having to mess with stuff. It's just sort of a syntax trick. It probably wasn't even necessary. I just used it to show off. Yeah, so the new, like, this is like a new place. It's like a temporary place, just so I don't overwrite what I want. Because changing a variable that is in a higher scope will change it. So I don't want to change it. I want to create a copy and then change that copy. So it's not really like that necessary to do the bracket thing, but whatever. Anyway, we set that place to 1. We're saying they're going to win the finals. And then we add the new hash in, assuming they'll win the finals. So it's a to the 1. And then set the map to be that. We can set it because even if we overwrite, we just need a valid sequence that corresponds to that hash value. So even if there are multiple, we only need one of them. So it's fine to just assign it. We do the same thing for if they lose the finals, so they'll be in position 2. And then put in the map. And this flag is saying if they win finals or not. I illustrated it like decently here. But yeah, that's how that works. Assuming it didn't get that many stalls. Yeah, it's not the worst. Considering my stupid penalty, that was pretty good. Considering starting like pretty late, doing dumb on C, and just explaining throughout. Yeah, like I said, I've been less and less concerned about penalty recently. I'm just more about like making the screencast like valuable and sort of trying to communicate more. Yeah. This was a pain. I should have done this better. I should have been more careful about this. But other than that, it was like relatively smooth. I mean, 20 penalty didn't end the world for me anyway. So yeah, it was more about solving F, but not that many people solved F, so I'm fine with not attempting that. Overall, I think it's like an educational round. I mean, the problems are educational. It's kind of what you expect. So I don't have that much feedback, or I don't have that much like commentary about the problems itself, or the problems themselves. But yeah, I hope this worked. Hope the microphone was fine, because I didn't use the microphone last time. Hope the fan was fine too. Yeah. So goodbye.